All right, let's go ahead and get started. Welcome back. So that first lecture was, an introduction, trying to get some of the tools introduced that we're going to be using. And this lecture is going to be basically introducing the first algorithm to do something real, something that can actually be used in practice. And then basically every lecture will build on top of this algorithm, extending it to more structured settings. But before diving in, I want to clarify a couple of things from the last time, from questions that came up, and maybe draw some pictures to make it more crystal clear what was going on in that last few minutes. So what we had in that setting was that n was equal to 2. And so we had two arms. And from each arm, we had that xit was iid from this distribution pi, and the expected value of this xit was equal to theta star I. Okay, for all t. And they were iid. And now what we did is we assumed that xit minus theta star I are one sub-Gaussian. And what that buys us is the ability to use sub-Gaussian tail bounds. Yes? Yes, I will try to write bigger. So this says xit drawn iid according to distribution pi. Expected value of xit is equal to theta star I. And xit minus theta star I are one sub-Gaussian random variables. And what that allows us to say is something like if I take tau samples from this random variable, from the ith random variable, or poll the ith arm tau times, then what we can say is the probability over 2 is equal to this. Okay? And this is known as a sub-Gaussian tail bound. And basically what it's doing is it's saying that if I have this picture where if this is theta I star, and if I take tau samples from it, its empirical mean, which I'm going to note this guy as theta hat I tau, meaning I sampled the ith guy tau times. And basically how he is distributed is something like looking like a Gaussian distribution. So this is the distribution I tau, where basically this width here is proportional to square root of 2 tau. So as, square root of 2 over tau. So as tau gets large, of course, the empirical mean converges to theta star I. Very intuitive. And it goes at this very predictable rate. And that's what this expression is saying, is a one-sided inequality. And in particular, this greater than epsilon. Basically, what this is saying is if this is this point here is theta I star plus epsilon, I'm integrating all this math and it's saying what's the probability that the empirical mean is greater than this value. And it's less than or equal to something that goes exponentially decreasing in both epsilon squared and tau. And so what we did last time was we said, OK, what I'm going to do for our first sort of approach at an algorithm, I'm going to have this algorithm that says, for t equals 1 to 2 tau, sample well, how about for the first tau times, I'll sample the first arm, and the second from tau plus 1 to 2 tau times, I'll sample the second arm. So sample both arms tau times, and then play argmax I theta hat I tau the rest of the time. And so the picture to go along with this is if I have my first arm, arms 1 and then arm 2, and these are the true means. So this is theta 1 star, and this is theta 2 star. The gap between these I'm calling delta. And by sampling each one of these empirical means, or each one of these arms tau times, and then building confidence intervals, I'm essentially picking confidence intervals that are defined like, I'm going to draw like this, where the width of this confidence intervals, where I know that the empirical mean, I'm guaranteed to have the empirical mean fall inside these confidence intervals for each one of these. And the width of this guy, the width of this confidence interval is going down like square root of 2 log 2 over delta over tau for each one of them. Because this confidence interval is a one-sided confidence interval, which means that if I set this equal to delta over 2, then basically just the probability that theta hat I is greater than theta 2 plus epsilon is greater than delta, or is less than delta. So the probability that theta hat I is greater than theta I plus square root of 2 log 2 over delta over tau is less than delta over 2. And if I do both sides, I get a two-sided confidence interval, and theta hat I must live within each one of these confidence intervals. And because each one of these is going down like 1 over square root of tau, I can have both of them hold, because this confidence interval holds just for this one. And so the probability that both of them hold, so confidence interval holds for both arms simultaneously, I can just put a 4 here. And now I have that both two-sided confidence intervals hold for both arms. And then the question just becomes, how big do I need to pick tau in order for these confidence intervals not to overlap? And so it just becomes, I just need to pick it down here. I just need to pick tau so that basically there's no overlap between them. And that value of tau is exactly that value of tau that we picked last time. OK. So moving on to the n-armed case, the problem with that algorithm that we ran was that picking this tau in advance required advanced knowledge of delta, or the gap, this big delta, which is never known a priori. And also, this only extended to 2 arms. So how do we make this algorithm go to n arms? That's what we're going to do today. So what I'm going to start with is by writing up an algorithm and then trying to analyze it. And so just bear with me for a moment while I write this up. And I'll try to make it as big as possible. So input, n arms, and confidence delta. And now for t equals 1, 2, and so on, I'm going to set epsilon t equal to 2 to the minus t. Sorry, not t, I want L. These are rounds, sorry. L equals 1, 2, whatever, LL, 2 to the minus L. And I'm going to pick tau L very specifically. Okay. So what are we doing here? What this algorithm is doing is basically a redux or generalization of what we did for this first very naive algorithm. We start the algorithm by just creating a set x hat 1, which is basically, let's just call that 1, just an index set of all the n arms. Okay, so everything's in the running now. And what we're going to do in stages, we're going to start discarding arms. And we're going to start to whittling down x hat L into a set that just contains essentially the best arm eventually. But remarkably, by doing this particular schedule, we're also going to have an algorithm that achieves near optimal regret because we're throwing things out at the right rate. And in particular, so what's really going on here is that we're choosing epsilon L in such a way that the confidence interval on theta hat computed just at the Lth round, and I'm doing something very sloppy here. I'm doing something very wasteful. I'm only using the samples to compute theta hat IL using the samples at the Lth round. Okay, it's very easy to use all the previous samples, but we'll see it doesn't actually matter. It only turns into a factor of 2. Yes?
After XL hat is tau L.
Tau. Here? Yes, tau. Tau L times. And so what we're trying to do is the way we're picking this epsilon L and this tau L is we're measuring every arm that exists in x hat L enough times so that its confidence interval is on the order of epsilon L. It's within a constant factor. And what this allows us to do is that essentially at each round, we're going to prove that an x hat L plus 1 or x hat L is always within a constant factor. Every arm in that remains has a gap of about 2 to the minus L or epsilon L. Okay?
This algorithm also doesn't know anything about the gap.
That's right. This algorithm doesn't know anything about the gap. It doesn't know. It's not making any assumptions on anything. Something that came up last time, without loss of generality, I'm going to assume, because I can always rescale things, that the biggest mean is less than or equal to 1, and for simplicity, that it is uniquely the best one. Okay, so it's just saying that all the means are between 0 and 1. You can always scale your problem so that you can do this. It's just a way of giving the problem some scale. And assuming that the means are ordered like this is just for analysis purposes. This algorithm, as you can tell, is completely permutation invariant to the indices. It doesn't matter. Any reasonable algorithm will have this property. So making this assumption that the means are ordered is without loss generality. And our goal is that for the best arm identification problem, we want to output the arm that is equal to index 1. OK. Yes?
Are we assuming a finite or infinite?
Good question. So for now, I'm not putting a cap on this. It's just going to go. And then what I'm going to prove is that there is some time that is verifiable. I can give you a certificate, at which time I'll return the best arm to you. And I'll prove an upper bound on that time. And I'll also say for all times, for any big T in the future, I will give a regret bound for that. And so the time in which the big T that we were talking about last time will come into view soon.
So T should be large enough so that we have identified the best one, right?
Not necessarily. And that would be an important part of the regret proof. That T does not necessarily need to be larger than the time in which the best arm is identified. That's the power of this algorithm is that you can get non-trivial regret guarantees before you've identified the best arm. That's important.
This is like sort of a binary search type of thing, because you keep increasing the time to search by a factor of 4 each time. But,
Yes, it's very much a doubling trick sort of thing, where I don't know what the gap is. So what I'm going to do is take this approach of take some number of samples, check if I can, check if I found the best arm. If not, double the number of samples, check again, and so on and so forth. And so if I do have means like this, where instead of having just two means, I have, say, if all my true arms, if my true means, they're sorted by assumption, look like this. In the beginning, my confidence intervals are going to be very big, right? Because tau L is relatively small. Tau L is increasing, is actually more than doubling. It's quadrupling every time, or every stage. And so in the first stage, all of the confidence intervals are going to be quite big. So on and so forth. But they'll hold for every arm. But the main point here is that this confidence interval on this best arm, we know that its mean is at least this big. But this guy's mean is no bigger than this. And so we can start to throw out, with just this small value of tau, we can start to throw out these arms and then only allocate samples. As this algorithm progresses, x hat L will hopefully only contain these arms with larger means that are closer together. And that's when it's really going to matter to get these confidence intervals really small. And so we're trying to do this sort of dynamic process. It's a very simple algorithm, but basically the techniques to analyze the regret and the best arm identification will be used for more advanced, interesting settings. Yes?
Obvious that this is going to converge to some singleton set?
No. It is not obvious, because if any of these confidence intervals fails, we could run forever. So if you had, so for instance, where this could fail, if my second and third arm had the same mean, and I for some reason threw out the best arm, and these had the same exact mean, or all the bottom n-1 arms have the same one, it will likely never stop. It will sample forever and never stop. Yeah. And more importantly, it will never output the best arm. And so it will just catastrophically fail. And so if we want to have a bound, an expected regret bound, we're going to have to take this into account.
If they're all different, then this will always output the best one, or someone.
If high probability bounds hold, yes. Yeah, I guess almost surely if they are all different, then this algorithm will terminate with probability 1. But if the means are same for some of them, then there's some possibility that it will go forever. Okay, so like last time, we're going to use an event-based analysis. What this allows us to do is we define some events, prove that they occur with high probability, and then do a deterministic analysis assuming these events hold. So let's do that. So define epsilon IL, or EIL, as the event that theta hat IL minus theta star I is less than or equal to epsilon L. So what I want in define E so this is an individual arm at time L, and E, big E without any subscripts, is assuming that they all hold for all time. Because what you can think of here is even though this algorithm is going to be throwing things out, I can sort of hallucinate that no arm is ever thrown out, and what would have happened if arm I would have survived to the Lth round and want this confidence bound to hold. And so what we can do is I want to prove that this thing is always, what is the probability this happens? Well, the probability that EIL complement is less than or equal to 2 times the probability for the two sides, theta hat IL minus star greater than epsilon L. But this value of epsilon L, this is just going to be less than or equal to 2 times this, just plugging in that tail bound, minus tau L, epsilon L squared over 2. So, since tau L is defined as the ceiling, it's at least this big what's inside the ceiling. And so when I have an epsilon L squared times tau L, these things are going to cancel. And then I'll just be left with 2 log 4L squared n over delta. But that's just going to be equal to, wait, and that's going to be these epsilon L's cancel, these 2's cancel, this log comes downstairs, and we get delta over 2L squared n. Minus? Oh.
There should be a minus 2 in the exponent.
A minus 2 in the exponent.
To get cancellation, we have something else.
So in front of the log, epsilon to minus 2.
Tau L is epsilon L squared, and I have an epsilon L squared here.
How's epsilon L equal to minus 2?
Yeah. Oh, thank you. These cancel, and I'm just left with this. And now the probability, what I can do now is just say the probability that E complement by a union bound is just less than or equal to the probability, is the sum over I equals 1 to n, sum over L equals 1 to infinity of delta 2L squared n. 1 over L squared sums to pi squared over 6, which is less than 2. And so this whole thing is less than delta. Okay? Okay. Yes?
So theta hat I sub L, L now stands for tau L or for L?
L I'm now defining, I'm defining it as this, so at the nth stage.
So it's like in the previous notation it would be tau L, right?
Yes. Yes, my apologies. Okay. So now that we have that E holds, we've got lots of nice things happen. So the first thing is that I want to prove that lemma, this is sort of like the core piece of everything, with probability greater than or equal to 1 minus delta, we have arm 1 is in x hat L, and the max I in x hat L, theta I star, is less than or equal, sorry, I want this to be the gap, is less than or equal to 8 epsilon L for all L. Okay? And the proof is quite simple. But once we have this, we're basically done. Yeah?
It's an empirical gap.
It's a gap that I've not defined. Actually. The delta, so gap I, big delta I, is just the gap between, the difference between the best arm and the ith arm. Okay, it's a positive number. And it's just the gap between the best arm and the second best arm. And then for delta 1, it's the gap between the best one and the second best. Okay, so this is so first note that 1 is always in x hat 1 because we initialize x hat 1 as all of x, or all of 1 to n. So for any j, we have that theta hat j, L minus theta hat 1L is equal to theta hat j, L minus theta star j minus theta hat 1 L minus theta star 1, where I'm putting suggestive parentheses, plus minus delta I, delta j. Okay, just using the definition of delta j. And now, each one of these by our event E is always less than epsilon L. So then these guys are less than or equal to 2 epsilon L minus delta j. But delta j is positive, right? So then minus delta j is negative, and so this whole thing is less than 2 epsilon L. But that's exactly what the elimination rule is. It's you remove any arm such that there exists some other arm that has an empirical mean that's at least 2 epsilon L greater than you. But we just showed that for any j, when I compare it to the first arm, the best arm, that gap, the empirical gap between the best arm and any arm, is always going to be less than 2 epsilon L. Therefore, the best arm will never be eliminated from the algorithm. Okay? So we've proven the first part of the lemma, where 1 is in XL for all L, because what we've shown is that 1 is in the first one, and it never gets removed by induction. On the other hand, for any I with delta I greater than epsilon L times 4 times epsilon L, we can do this again, where the max, the elimination rule, just writing it down, well, I don't know which one he's going to pick here, but the one using the algorithm is the maximum empirical mean. But we just showed that 1, the best arm, always is in x hat L. And so because of that, I can lower bound this maximum empirical mean by the empirical mean of just the maximum, of just the one from the best arm. And by the same sequence of steps of adding and subtracting the true means, I can get that this guy is at least equal to minus 2 epsilon L plus the gap. But the gap is at least 4 epsilon L. And so this whole thing is at least 2 epsilon L, meaning that we have removed any I in x hat L with a gap that's at least 4 epsilon L is thrown out on the next round, meaning the maximum gap in x hat L plus 1 is less than or equal to 4 epsilon L. And 4 epsilon L is equal to 8 epsilon L plus 1. Therefore, we have the claim. OK? Is that clear for everyone? Because this argument is going to be made quite a bit and get more complicated as time goes on. So it's important that this is crystal clear. Okay. I apologize if it's going. Yeah.
So you define delta 1 to be 0 then?
No, I define. So this is the absolute. I'm sorry. That's why we don't do that. And then if delta for I equal to 1, delta 1 is equal to delta 2. It's the minimum gap.
Minimum gap is some constant thing, then how can you have it less than 8 epsilon L for all of them?
Well, it's important that I made this assumption that there is some finite gap between the best and second best arm. So delta 2 is a finite number. And so yeah, sorry, what was the question?
So if delta 2 is, for example, 1 over 5,
Mm-hmm.
right? Then for epsilon, for L large enough, this thing is less than 1 over 5.
Yeah.
But all of the delta i's are more than 1 over 5.
Yes.
So,
Th- Okay. We would have, so in that case, I'm just counting, so all the arms with gap greater than some number will be thrown out that are not the best arm. The best arm will not be thrown out because of this. So this is just saying that the best arm will never be thrown out. And maybe there's a notational sort of contradiction here. Because, yeah, any I not equal to 1. Okay, any I not equal to 1 will be thrown out this way. Is that clear?
Could you go through and explain what we can't really read the subscripts.
Can you make the J's and the 1s clear?
Yeah. Okay. For any I not equal to 1, okay. Now what I'm going to do, the argument here is that 1 is in X hat L. We just proved that for all L. Therefore, I don't know what this value is. This is the stopping condition, or this is the throw out condition. But I don't know which one this is going to be. But this is the value that it takes is the maximum one. And so I can upper bound this, or sorry, I can lower bound this by just using the empirical mean of the first one. Right? Is that clear? And now I can do the same trick over here. This is greater or equal to 2 epsilon L plus delta I, and delta I is greater than 4 epsilon L. And so this whole thing is greater than 2 epsilon L. And so this arm will be thrown out. For any I that satisfies this will be thrown out. Therefore, the only arms in XL plus 1 will have gap at most 2 epsilon, and any arm in XL will have gap at most 8 epsilon L, because epsilon L is equal to 2 to the L, or 2 to the minus L. Happy? Okay. The fun part. Okay. I'll begin with the regret bound and show you that it doesn't matter that t can be smaller than the time it takes to identify the best arm. So what I'm going to do, what we showed last time, was that the expected regret, is equal, going to be written as the expected value, where the expectation is taken with respect to the randomness of the algorithm and the randomness of the observations. Here our algorithm is deterministic. Okay, the delta i's here are deterministic, but the ti's are random because they depend on what the algorithm did. And now what we can do is I'm just going to upper bound this guy with high probability. Okay. Because on event E, I never have arms that are worse than 8 epsilon L in XL. And that's going to be helpful for limiting how much regret I can actually incur. And now, something to worry about, though, is that for any nu greater than or equal to 0, just some constant that I'll specify later, but for any nu greater than or equal to 0, we have that this regret is less than or equal to nu times t plus the sum over L such that 8 epsilon L greater than or equal to nu is less than 8 epsilon L tau L x hat L. Right? Because what I've assumed on event E, that no guy in x hat L has a gap bigger, or has a gap bigger than 8 epsilon L. And so I'm upper bounding simultaneously the gap in delta I on each round L like this. But what I've done is I've split it up into two pieces. I've split it up into, for small nu, what's going to happen is that this term, if nu is extremely small, like so nu is equal to 0. If nu is equal to 0, then this is just summing over all rounds, the regret incurred from all the arms in every round. Okay? But if nu is greater than 0, what it's doing is any arm that's being in this summoned, where 8 epsilon L is less than nu, is basically getting captured by this guy here. And so I'm breaking it up into what are the gaps and where am I incurring regret. Okay? And so this is an upper bound. And then what I can do is then note that once L, if L is just the index of this algorithm, once L is greater than log 2 of 8 epsilon L, I know that L can never be greater than log 2 of 8 delta, because at that point, once L is greater than this number, that means there are no arms in x hat L by definition, right? Because of our event, we have that, or because of our lemma, once L, because epsilon L is equal to 2 to the L, so once L is greater than the ceiling of 8 times, or once epsilon L is greater than log 2 of the min gap, we have, so I'm defining delta now, I should just call it delta 1, as just being equal to the min gap, basically, delta 2. But I use this notation because it's kind of simpler. So what I was calling delta 2, or the min gap, I'm just going to say delta like that. And because once L is greater than that, the only thing that, by our events, the only thing that's in XL is the best arm. There exists no arms better than that because that's what our events say. Right? Is that clear? Yes, it's coming. And excellent point. Why is it 8? It's 8 delta because once L is greater than or equal to this, then epsilon L is going to be less than or equal to, so for this L, we will have that in that round, epsilon L will be equal to 8 epsilon L. 8 delta, yes, sorry, 8 delta. And that is precisely what this guarantee is saying. That 8 from here is coming from this 8 here. I have to pay a little extra. I have to go 8 times that log 2 of 8 delta instead of just log 2 of delta, because I have to pay for the fact that once I hit that min gap of log 2 of delta, because I only were sloppy, only went up to a factor of 8, I still have to go 3 more rounds in order to get to the min gap. Okay, it's
1 over 8 delta.
Sorry, 1 over delta.
Shouldn't it be delta ITI on the left-hand side?
Sorry, yes. Where Ti is the number of times that the ith arm has been pulled up, at time big T, this time T. So the sum over all I of Ti is equal to big T. Okay, and so like a student pointed out very conveniently, it's actually won't go smaller than nu, so it's actually the max of delta in nu inverse ceiling. Because this sum, because of this guy here, I'm only summing over those L's that are bigger than, so 8 epsilon L is greater than nu, and that's exactly equal to this. And so you'll never go further than the max gap, you'll never go further than, or the min gap, you'll never go further than nu. I know this sum is a little hairy, but I promise you, if you work out the algebra, it will work out. Okay. So we have that guy there. And now what I can do is I can rewrite this x hat L as just a bunch of indicators. Is a sum equals y to 1 to n, but it's actually 2 to n because I incur no regret on that first one. Of the indicator that delta I is less than or equal to 8 epsilon L. But then that condition, by replacing this, so I've replaced x hat L with just those guys that have gaps less than or equal to 8 epsilon L. This is coming directly again from our lemma. Because the only guys that are in x hat L have gaps that are less than or equal to 8 epsilon L. And by doing this, we again get this nice factorization. The same way we move the nu up into this log and move the gap up into this log, when we sum over L, if we exchange these sums, the only L's that are going to be on, where this condition holds, is up until the value of L that this is on for. So if I solve for the L, which is this, when this is on, it's only going to go down to the value of delta I. And so then I can rewrite this as I equals 2 to n of the sum L equals 1 to log to 8. Now I'm going to say delta I max nu inverse ceiling. And then I have, again, 8 epsilon L tau L. So all I've done is move this indicator up into the summand. Okay? I've just changed the limits of the sum. And this is convenient because now I can just plug in my value of tau L, which is equal to this guy here. And it has this very nice form of epsilon L minus 2 and epsilon L. And I know that, so if I just plug that in, one of the epsilon L's cancels. And I just get times, ignoring integer effects, I'll just put it into the sum and give myself an 8. So I just get 1 epsilon L of, I guess it's like 4e L squared n over delta. Okay? And now what I'm going to do is this sum from L equals 1 to this big sum means that each one of these L's in here is less than or equal to the maximum sum, the limit, right? So for this log, I'm going to plug this value into this value of L and pull this logarithm outside. And then what I get is nu t plus I equals 2 to the n. I pull these things out. I get 16 log 4e, annoying constants. And then this big guy, log 2, 8, delta I max nu inverse ceiling squared. That's pulled out. N over delta. Okay. And then I finally have that it's just the sum of L equals 1 to this thing up here of epsilon to the minus 1. This guy right here. But that's just equal to 2 to the L. Because epsilon L is equal to 2 to the minus L. And so I just get this as 2 to the L. And now I use the geometric sum. To the n plus 1. And then I get this result, that this guy just gets plugged into this value here. And so the final result the E came from the fact that the ceiling of A log of B is less than or equal to A log B plus 1. And then if A is greater than 1, then I can always up around this by A log EB. Just algebra. I don't want to deal with ceilings. And then so what I get at the end is that this whole expression is then bounded by nu t plus the sum over I equals 2 to the n of some constant that I'll leave unspecified, but you can compute it. Times n. Okay, we're almost done. So what we realize is that now I just copied that from over here to here with the constant c. And now when nu is equal to 0, this implies this term is going to be 0, obviously. The max of delta I in nu is going to be delta I. And this implies that the sum over I equals 2 to the n of delta I ti is less than or equal to the sum over I equals 2 to the n of some constant delta I minus 1 log n log delta I over confidence delta. Okay. And now, what I can do with this is that if I plug in, just like we did last time, of delta equal to 1 over t, then I get that the regret RT is equal to this guy under the events holding, under E holding, plus it not holding. And so it's going to be, by the same sequence of events, this guy here, 2 to the n. I'm going to plug in my delta equals 1 over t here. T is going to be, well, I won't write it. I'll just do it out. Delta I minus 2 log n log delta I minus 1 times t. It's the big factor that we care about. Plus the probability of failure, which is delta times t, like last time, but delta was chosen to be 1 over t, and so this is just a constant factor of 1. And so what we proved is that this algorithm has logarithmic regret. And that constant, so I can, for large enough t, this log term and this n term gets swallowed into the big T. And so what we really have is log t times the sum of the inverse gaps. That's why it's 1, not 2. Okay. However, we can play the exact same trick. If we don't set nu as equal to 0, if we set nu as equal to, if we use the fact that nu is always going to be greater than, if we use the lower bound, that nu greater than max delta I is always greater than or equal to nu, and just optimize over nu, then this whole expression just becomes nu t plus all these delta i's just go to nu's, and we just get some other constant of n nu inverse log n log nu inverse over delta. And if we optimize over nu, because this is always going to be true, this is true for all nu, and then we add in our trick of the expected regret is less than delta t for any delta. Once I optimize over this value of nu, what I get is something that is some constant n t log n t. Okay? RT is less than or equal to this, using the same sequence of steps that we did last time and this time. Okay? So what we've shown, both these regret bounds hold simultaneously. You get to choose one, right? You get to take whichever one you want. And most importantly, this regret bound holds for all values of big T. So that when big T is smaller than the sum of the inverse gaps, say before you can actually identify what the best arm is, and doing that identification proof is very straightforward. It's a little easier than this proof. Maybe I'll put that on the section handout. But the point is that when big T is very small, not big enough to actually identify the best arm, you're still getting sublinear regret. Because this is square root of nt log t, and it's independent of gap. And so this is called a distribution-free regret bound, because it doesn't matter what the gaps are. But then we know that once we hit this magical time where we can actually identify when we actually identify the best arm, and it actually kind of comes out of this proof if you squint at it and you're careful with these steps and figure out, well, what is that time in which this bound actually kicks in? It kicks in exactly when t is bigger than the sum of the inverse gaps squared log inverse gap over log n, or over log 1 over delta. And so what we have is, for small values of t, the regret is scaling a squared of nt, and for large values of big T, the regret goes into this regime of logarithmic in t. And so we get this nice sort of phase transition from I don't know what I'm doing, but I'm still doing sublinear regret, to I've now found the best, and I'm getting logarithmic regret. Is there any questions on this?
What happened to the log, to the square on the ceiling going from the left hand towards the right hand?
This here?
Yeah.
Because it's in the log, I can just square everything. I can put a squared on everything. And then log of a squared is equal to 2 log a. So it just gets eaten in the constant.
Oh, okay. Maybe it doesn't matter, but when we have a radical n inside the log.
So I can always upper bound something by a higher polynomial and then just bring it outside because it's just constants. Okay, in the last few minutes, yeah.
Did you put delta 1 over t in the last line as well? I missed that.
Yes, so I have this regret bound for any value of nu, and then I'm going to optimize over my value of nu because it holds for any nu, and that turns out to pick something that's like this with a delta down here. And then I do my expectation trick where I do basically the sum of all, this holds with high probability on my event E holding, this holds with my event E holding, and if the probability of my event E failing is less than delta, and if the event fails, I incur regret t, at most t, and so the expected value of the whole regret is the regret if the event holds plus the regret if the event does not hold. And so I just put in delta is equal to 1 over t. Okay, so this proof, unfortunately, is improvable in many ways. So first of all, it's this factor of delta. You have to be able to choose big T ahead of time. This is a big annoyance because a lot of times you don't know what the horizon is. There exist other algorithms where you don't need to know this. In particular, one algorithm we'll talk about in section is UCB, upper confidence bound. And that will not require knowing the horizon length. But then there's also other things we can improve here. It turns out that this log factor here is unnecessary. You can remove this. And you can prove an anytime, or so you can prove a distribution-dependent bound that is just square root of nt. This was done by Moss, by Audebert and Bubeck several years ago. This log can go away. In terms of our upper bound, basically this is tight. It's tight up to constants, meaning that this regret bound really cannot be improved upon in such a way such that as big T goes off to infinity, this factor here in terms of problem-dependent parameters is optimal up to constants. We have an unspecified constant c here. If you push it through, I think it comes out to be like 512 or something, some egregiously large number. The optimal constant is 2. And there exist algorithms that achieve this. The analyses are complicated, but the algorithm that achieves it is not, and that is UCB. And we will open with that next time when we talk about lower bounds and how we know that what we're doing is on the right track here. And next time, we're really going to talk about more structured settings and start to introduce feature vectors and things like this, which will be lead us more into recommendation systems and things like that. OK, thank you.